course today, I'm actually going to be walking you through another exciting and fascinating topic in statistics. Give me 1 second while I pull up my screen. Okay, so like I said, today we're going to be working on the concept of convergence. So the statistical principle around convergence will actually be the focus today. And of course, I'm going to be guided by this outline where I'm actually going to walk you through statistical models, properties of good estimators, and lastly, we actually are going to have discussion on asymptotically relative efficiency of estimators. Okay, so we're actually going to start the day with a statistical model. But you know what? Before I go into statistical model, I think I would like to have a kind of reflection on the use of model, you know, in this world. Now, let me tell you, the appearance of a physical world is actually independent of human knowledge. And you know what? As human beings, we need information, we need knowledge to understand situations around us. We may want to understand medical environment, we want to understand political environment, we want to understand the economic environment, we want to understand everything around us because we actually want to be in control. And for us to be able to understand situation around us, we actually need to go mathematical. Okay, so going mathematical, we actually going to use we normally use model, you know, so we use this model to model situations around us. And what do we mean by model? Model is a mathematical or statistical, representation of reality. Okay, which means we modeling is a process by which we actually convert reality into mathematical expression. Now, broadly speaking, I'm actually going to say that model can be divided into two. We have statistical models, and of course, we have deterministic models. But you know what? What we mean by statistical model, the statistical model actually uh, is a combination of deterministic and a stochastic parts. Now, what do we mean by stochastic parts? Our knowledge, our belief in statistics is just that even though we want to understand situation around us by trying to model reality, the fact remain that model cannot be the same as reality. Okay, because we don't expect every you know variation, okay, in the reality to be explained by a model. Okay, so we acknowledge the fact that there's always going to be what we call information loss. There's always going to be an error. We cannot get 100% of the information that we want using the model. Okay, so we are, by incorporating stochastic model, which I call statistical model, we have actually acknowledged the fact that, model cannot be the same as reality. And because of that, we're going to define statistical model, is a family of probability distributions. Of course, Probability only thrive when there is variation, and of course, because we're talking about randomness, because we're incorporating randomness into our model, of course, uh, the model is said to be probabilistic in nature. Okay. Now, a parametric statistical model, on the other hand, is actually a family of probability distribution, okay, specified by a finite set of parameters. Okay, we're looking for information as human beings. We want to get information from population. Now, the question now is the populations from which we actually want to get information from these populations, we need to know the probabilistic description. Because of that, uh, every population has probabilistic description. And of course, the probabilistic description that I'm actually talking about is a function of parameters. Okay. And what do I mean by parameters in the first place? Of course, the parameter is a population characteristic value that we actually want to determine. Anything that we want to know that we don't know, okay? Of course, initially we're modeling because we're seeking for information because we actually want to understand our environment, and that is why we need information. And that is the reason why, um, the population through which we are seeking to get information, we need to be able to understand the probabilistic description, which is what we call probability distribution. Okay, so that's exactly what I'm trying to talk about here. And you know what? There's a numerical quantity, okay, that can be specified for any given probability distribution in the family. And of course, these are the information, that we're actually seeking for. We'll be seeking for the information about mean, about median, about variance, about upper quartile, about lower quartile, about range, and so on like that. For instance, I may be interested, probably want to get what is the average allowance, or what is the average household income in the United States of America or in a particular country. Or I may want to know the median of that, the maybe probably, or maybe the median time to cure, uh, you know, variability, and so on like that. Those are parameters. And of course, these are actually uh, specified as part of the probabilistic description of the population that I'm talking about. Okay, I want to first to focus on parameters right now. The essence of going into a population is actually to figure out the values of parameters. What do we understand by parameters? Parameters are population characteristic value that we seek to determine. It could be mean, it could be variance, it could be standard deviation, it could be ratio, just like it could be proportion, just like what is happening in the world right now. We are, the three major companies, two in the United States and one in the United Kingdom, have actually claimed to have developed vaccines, that can actually be used to prevent COVID. Okay, looking at these vaccines, looking at the claim, one of the company, Pfizer claim they are, the efficacy or the efficiency of their vaccine is 95%. And Moderna also claimed the same. And the AstraZeneca in the United Kingdom, particularly in the University of Oxford, actually claim a 70% efficacy rate. Now, these are the hypothesized values of parameters because, you know, it's a claim. because they've conducted a series of clinical trials, and I believe they did not study the entire population. Okay, so before they conduct the the clinical trial, of course, they were also looking for the value of parameter, which is unknown to them. I mean, the efficacy rate of their vaccine was unknown to them until they conducted a series of clinical trial to come up to, or to come to term with the values that they actually claim. Okay, so I'm just trying to tell you that, trying to give you an example of parameters. And of course, I told you the other time that the population through which we actually want to carry out investigation uh, is probabilistic in nature. Okay, and we actually need to understand the probability distribution of a given population, from which the data set is actually going to be drawn. Okay, now what I stated before I go into that, we have some symbols that we actually use to denote, population parameters. Okay, of course, we have what we call the mean. We use this is a symbolic representation of the mean. This is standard deviation, and of course, in general, we use that symbol theta. The theta could be mean, could be variance, could be standard deviation, could be proportion, could be whatever uh, characteristics of interest that we are seeking information about. Okay, and then uh, statisticians actually uh, uh, consider some probability distribution like Bernoulli, like binomial, like geometric, the negative binomials, normal distribution, beta distribution of the first and the second kind, the Gombe distribution, the Nakagami distribution, and so on like that. Okay, but you know what? We have a way they specify parameters in distributions, in every probability distribution that is parametric in nature, of course, every parametric distribution, of course, is probabilistic. Okay. And of course, we have a way we actually denote parameter. Okay. At times, like I said, most of the time, we use data, and of course, in some probability distributions like discrete, where the interest is probably on proportion, we could actually write theta to be p. And that is the reason why, if you take a look at Bernoulli, we say the parameter is p. If you look at the binomial, the parameter is p. If you look at the geometric, the parameter is p. And if you look at the negative binomial, of course, we have the parameter. So part of the parameters that we have is actually p. Okay, so take a look at that. Take a look at what we have right now. So we have probability distribution actually defined in terms of parameters of interest. Okay, the next thing I actually want to talk about now, what do we mean by statistic? Excuse me. Of course, we are actually looking for parameter. Okay, that's what we're looking for. It's unknown. And we believe that this is a population characteristic value. But you know what? There's no way we can actually examine all elements in the population. We got to take a sample size. We're going to take sample from the population because we have already justified, statisticians have justified, taking sample from population. Because of that, the unknown population parameter we want to obtain, okay, is not actually going to be, we're not going to obtain the true value of the parameter. But what we're going to end up getting, we're going to end up getting an estimate of the parameter. And how are we going to get the estimate of the parameter? Of course, when we take a sample from the population of interest, considering the probability distribution of the uh, population area, of course, we can actually determine uh, the parameter from the sample. Okay, so and that is the reason why I say a statistic this time around is actually a numerical quantity. Okay, a numerical quantity that we actually determine from the sample and determine it from the sample, and that is the reason why we said it's a function of data. A function of data because the data we are collected is actually uh, a sample taken from a target population. So statistic should not be seen as a parameter, but it can only be seen as probably an estimate of the parameter. Okay, so if it's an estimate of the parameter, of course you need a lot of things have to be done to ascertain its validity, like to ascertain its you know whether it is actually represent the parameter, the value of the parameter we're seeking to get. And of course, using different kind of data, like if you take different sample size, you're actually going to have different statistic computed. And that is the reason when you look at one of the company that claim to have developed vaccine, I mean the AstraZeneca in the University of Oxford in the United Kingdom. Of course, the clinical, they actually have series of clinical trials they perform in one, they have 90% efficacy, in another one, 75, in another one, they have 70. Of course, you know that statistic actually vary around sample. You know what I mean? Okay, so because of that, and that was why I said statistic can be calculated from data for a problem, and even though the true parameters values are unknown, the fact still remain that we don't know the efficacy or the efficiency rate of you know the vaccine. Okay, and which is unknown. And you know what, the only thing that can make us to be rest assured is that what we don't know, of course we can actually figure out by taking a sample of data, okay, which is the clinical trial they are doing right now. The clinical trial they have conducted, of course they're making use of samples. Okay, the next thing I want to talk about now, I want to talk about the example of statistic. Of course, when I refer to statistic, is actually is an attribute of sample, and that is why we actually gonna. If I'm looking for population mean, okay, using a sample data, I'm actually going to end up getting the sample mean. Okay, take a look at that. That's an X bar. That's a sample mean. If I'm looking for population variance, and if I have a sample of data at my disposal, what I'm going to end up is sample variance. Okay. And the same if I'm looking for median as well, if I have sample at my disposal, what I'm actually going to end up getting is a sample median. Okay. So take note of that. Okay. So now the next thing I want to talk about the estimate of parameters. And of course, we what we actually estimate, what we obtain from data. Okay, we're actually going to assume that to be the values of the parameters we actually want to get. Okay, so therefore they are the estimate of parameters. Okay, so the if theta is a parameter, which is which could be mean, which could be variance, which could be standard deviation, which could be proportion. Okay, and of course the statistic, it's actually going to be theta cap. So the theta cap is actually going to be the estimate of that. Okay, the statistic theta cap is going to be the estimate of that. And why is it an estimate of that? Is because the statistic theta cap actually we is a function of data, and this data is we're not using everything, we're not actually uh you know enumerate or every item in the population. Okay, and that is the reason. Okay, and specifically, if a population mean is a parameter, of course the statistical mu cap is actually going to be the corresponding estimate. Okay, now I think I said something the other time that we have different kind of probability. When we have different populations, of course, we're actually going to have different probability distribution. Okay, different population will exhibit different probabilistic description of reality in that population. Okay, so suppose we actually want to estimate the population mean using the sample mean, okay, as an estimate. So when n is large, okay, what happen? When the sample size is large, what happen? Of course, according to the central limit theorem, even though the population that we are sample from, if the population we sample from is not normal, okay, if the population we sample from is not normal, of course, taking the last sample, of course, the the estimate the sample mean, of course, will be approximately normally distributed. Now, let me just tell you that the different kind of probability distribution that we have, that we talk about, normal distribution is part of that, and of course, a normal distribution is more or less, every other distribution, every other probability distribution in statistics actually look up to normal distribution, because with normal distribution, we believe, um, the variance, okay, we actually going to be fantastic. But let me tell you this. Uh, uh, that actually depends on what you want to figure out. Whether normal will be, when you are given a particular probability distribution, okay, whether normal is actually going to be good, or a different distribution is actually going to be good. That depends on the parameter that you are looking for. So I'm still going to talk about that as time goes on. Okay, so what I'm trying to talk about right here is just that, okay, uh, if we actually want to estimate the population parameter mu using the sample mean, okay, when we take a very large sample size, of course, we expect the distribution of the sample mean to be approximately normal. And of course, approximately normal actually mean the mean of the sample mean is actually going to be this guy here. Okay, the mean of the sample mean is going to be that guy there, and the variance of the sample mean is actually going to be sigma squared divided by n. Okay, so sigma squared divided by n, and of course we can have a way to estimate both parameters in this distribution, which is the parameter mu and sigma squared. Okay, the next thing I actually want to talk about now, I want to talk about properties of good estimator. Of course, I'm going to tell you this. Estimator is a particular formula that we actually use in estimation. And of course, estimation is a process, through which we actually want to, we're using the sample information, you know, to actually take a decision regarding the value of a parameter. Okay. So, estimator is that particular formula, okay, that we use, okay, in an estimating process. Okay. And you know what? The estimate is a result that we obtain using an estimator. So, like I said, estimator is a formula or method that we use in estimation. And you know what? Why do we need to care about how good an estimator is? Of course, we need to care how good an estimator is, because the moment the formula or the method you are using is wrong, of course, you expect the result that you're actually going to get to be wrong. That is going to be giggle, garbage in and garbage out. Okay, the moment you use a wrong result, a wrong method, you use a wrong estimator, you're going to end up having a wrong result at the end of the day, a wrong estimate at the end of the day. And that is the reason why we actually need to know what are a good property, an estimator should have. Okay. Now, number one is actually what we call unbiasedness. And of course, for unbiasedness, what we're actually talking about is that we expect, you know, uh, the expected value of an estimator, okay, should be equal to the true value of the parameter. The fact remain that we could have different kind of estimator. We could have different kind of estimators in the and I told you the other time that statistic vary from sample to sample. Okay, statistic vary from sample to sample. Okay, so uh because of that, but the mean of the statistic, okay, the mean of the estimator that we talk about should be automatically the true parameter we're looking for. Because some of you may be wondering if the parameter we're talking about is the efficacy of the COVID-19 vaccine. Of course, now you're going to be asking why, how does a Pfizer company arrive at 95% efficacy rate? Of course, they arrive at 95% efficacy rate, you know, by try because they conducted series of clinical trials, where different samples of people were used in their study, and of course, they recorded for each sample they have the efficacy rate, and of course, so for the particular sample they have this efficacy rate. For the other sample they have this efficacy rate. Of course, for them to arrive at their efficacy rate right now, they're actually going to find the average of that. Okay, so believing that the expected value of the estimator right here is actually going to be equal to the population parameter. Now, because of that, we're actually going to say the parameter. I mean the estimator is unbiased. Okay, another very good property of an estimator is what we call consistency. And what do we actually mean by consistency? The consistency is actually focusing on last sample. Okay, when n is large, in such a way that it tends towards infinity. What is our expectation? Our expectation is that the estimator theta cap should actually approach the population parameter, should approach a true value. You know, some of us, I've listened to some of my students that argue that instead of us to, that since we know that when we work on the large samples, why can't we be focusing on, population instead of taking sample? Of course, we know that we're not only looking for efficiency, where you are, but we're also focusing on the cost and efficiency. Okay. And we believe that using, taking a sample size from population instead of study the entire element in population, there's a way we can actually, minimize costs of sampling. And there's a way we can also attain efficiency. Okay, so but the fact remain, as the sample size increases, as put forward by central limit theorem, of course, we expect estimator to approach the true value of the parameter. Okay, now in probability, you understand what I mean? So in probability, that's our expectation. Now, when the other time, uh, when I was giving you different kind of sample statistic, I make mention of sample mean, I make mention of sample median, I make mention of sample variance. So which means when n is large, okay, when n is large, mathematically speaking, we say when n tend to infinity. We're not trying to say n equal to infinity, but we're trying to say n, the sample size symbolically represented by lowercase n, is sufficiently large. Okay, so when it is sufficiently large, the sample mean will be a consistent estimate of the population mean. When the sample median will be a consistent estimate of the population median, and the sample variance will be a consistent estimate of the population variance. The sample median will be a consistent estimate of population median. You understand what I mean? And that's exactly what is actually, that's what we're trying to talk about right here. Okay, that is when we're taking large sample. So we expect all the sample statistic to be a consistent estimate, not just an estimate. It is not all estimates that are consistent, but of course, this is a statistical way to to investigate any estimator for consistency. Okay, the next thing I actually want to talk about now is what we call convergence in distribution. What do we mean by convergence in distribution? You know, uh, according to central limit theorem, of course, we when you take a sufficiently large sample, even though if a population is not normal, of course we expect that the population to be approximately normal. Okay, so there's one thing that we call one of the properties of a probability distribution that we call CDA. Okay. Now, uh, when then when convergence in distribution is just a situation whereby the CDF of one distribution actually converging to the CDF of another distribution. But you know what? The convergence don't just occur, but we have a kind of a prerequisite. There's a prerequisite. Okay, there's a requirement for convergence to occur, and which means when n tends to infinity, okay, when n tends to infinity, then we expect the CDF of a particular probability distribution to converge. If you take a look at binomial and Poisson distribution, binomial lead to Poisson distribution. So it means if I work on the CDF of binomial, of course, if I obtain the limiting, if n is sufficiently large in binomial, so it means if I take the limit of the CDF of binomial, the limit of the CDF binomial is actually going to is going to converge to CDF of a Poisson distribution. That's exactly what we're talking about. Okay, so, and that is what I said. Xn converges in distribution to X. That's exactly so. And a simple example is that the empirical CDF obtained from sample converges in distribution to the distribution CDF. Okay, now the next thing that I actually want to discuss today is what we call asymptotically relative efficiency of estimators. Now, what do I want to talk about right here? What I actually want to focus on here is this. If I have a normal distribution now, and I actually want to figure out average, okay? Maybe I want to figure out the average of maybe the average average household income in a particular country, or I want to figure out the average of certain characteristics of interest. And I know the probability distribution. Okay. Now the question now is we have three ways to measure average. Okay, mean, median, and mode. Okay. Now if what is the appropriate measure? Okay, like if I have a normal population, if I have a normal distribution, and I actually want to figure out an average, should I use mean or median? Okay, that is what we want to focus on here. Okay, where we actually want to investigate them, asymptotically. Okay, when the sample size is large. Okay, which of the two measures do I need to use given a baseline distribution, given a normal distribution? Which one am I likely to use? Okay, it's actually going to lead to gain in efficiency. Now, when I talk about gain in efficiency, I'm actually going to be talking about, um, the one with a smaller variance. Okay, and that is why we're actually going to, compare the variances of the two measures, given a baseline probability distribution. So, given a normal distribution, what is the best measure to figure out the average? Is it the mean or median? Or given a Laplace that we also call double exponential distribution, which one is a a good measure out of the mean and median. Okay, and that is exactly what I'm actually going to discuss with you right here, so that you don't just use a particular measure. You have to, number one, you have to take into consideration the probability distribution. Okay, for you to be able, so that for a given probability distribution, if you want to figure out the average, okay, you'll be able to know whether you're actually going to use mean or median, and that is actually going to be uh, the focus. Now, because of that, I'm actually going to share a new screen. I'm going to share my whiteboard right now to be able to discuss, to show example of that. I'm actually going to share my whiteboard. Okay, this is my whiteboard right now. I believe you can see my whiteboard. Okay, let's say for instance, we actually focusing on normal distribution. Okay, now focusing on normal distribution, if we have identified a population to have a probabilistic description that's actually look like that of a normal, that we call normal distribution. Okay, so now if this is what we have, okay, and we are thinking of course, when you have a normal distribution, f of x equal 1 over square root of 2 pi sigma squared exponential raised to power minus half x minus mu uh, over sigma, okay, squared. And of course, x lie between negative infinity and positive infinity. Okay, now when you take a look at this, of course, the parameter here, okay, the parameter here is actually theta. It's actually mu equal to theta. So if I actually want to rewrite that, I'm actually going to write 2 pi sigma squared uh, exponential raised to power minus half x minus theta sigma squared. Of course, I know there are two parameters, but right now we're only seeing mu as a parameter. Maybe probably sigma squared is constant. Okay. Now, if this is what we have, the variance, you know, maybe this is the probability distribution of the population. And of course, we actually want to compare. And there are two estimators that we actually want to compare. We want to compare the median, okay, and the sample median and the sample mean, okay, and the sample mean. We want to actually compare these two estimators. We want to see which one is better, okay, to use if we are sampling from normal probability distribution out of the median and mean. Okay, and so for us to do this, what we actually need to do is to look at them relatively. Okay, and that's what I call asymptotic relative efficiency. So what is the efficiency of one estimator to the other? And that's exactly what we actually going to talk about. Okay, so if that is what we're going to talk about, then it means I need the variance, okay, of the median, okay, and I also need the variance of the mean, okay. I need the variance of the median, and I also need the variance of the mean, okay. Now, I'm going to clean my board. I'm going to clean this side right now. I'm going to clean this side right now. Okay, so now, if I, if you, the variance of the mean, okay, the variance of the mean is actually sigma squared over n. Of course, we know that that is the variance of the mean, given normal distribution, okay, the variance of the mean is down. But if you want to find the variance of the median, of course, we're actually going to use 1 over 4 f of theta, or or squared. Okay, we're actually going to use And then, for one observation, okay, because what happens to one observation will automatically happens to or to more than one observation. So because of that, I'm actually going to be using just sigma squared. Okay, I'm going to be using, which is more or less talking about, okay, never mind. So uh, let me do this. Okay, so for n, let me put n there. Okay, so this is the variance. We have the variance of the mean, and we need to determine the variance of the median, okay, from the distribution. Okay, so what I'm going to do right now, this is what I'm going to do. So what I'm going to do right now, uh, given a normal distribution, so I need to first obtain the variance of the median. Okay, I need to obtain the variance of the median. Okay, so the variance of the median, okay, the variance of the median, like I said, is the formula you're actually going to use is 1 over 4n f of theta or squared. And of course, f of x, the normal distribution is actually 1 over square root of 2 pi sigma squared. Give me 1 second. 2 pi sigma squared exponential is power minus of x minus theta divided by sigma all squared. Okay, so what I'm actually going to do now, I'm actually going to plug in theta, okay, into wherever I see x, of course, to be able to get the f of theta right here. And of course, I'm actually going to have 1 over 2 pi sigma squared exponential is power minus of, okay, theta minus theta that squared. And when you take a look at that, that will be exponential is about 0, and that is actually going to be 1. Okay, so if it is 1, it means what I'm actually going to get from the f of theta is actually going to be that. Okay, so if the f of theta is going to be that, uh, then I can get the variance of the median right now. So the variance, okay, of the median is actually going to be 1 divided by 4n. Okay, then the square of, so I'm going to put 1 over square root of 2 pi sigma, okay, or squared. Take a look at that, okay, or squared. Okay, so let me clear my board. So r squared. So what I just need to do now is just to simplify. Okay, so like I said, for you to do well in statistics, you need the knowledge of mathematics, because you need the knowledge of algebra, and that's exactly what I'm doing now. I'm simplifying. Okay, now uh, so I need to simplify this guy now. So I'm actually going to have 1 over 4n and 1 divided by 2 pi. Let me take a look at that. Okay, so this is a 2 pi sigma squared. So 2 pi sigma squared. Okay, so when you square that, okay, so, and of course, if that is exactly what you have, so this time around, this is going to be the same. 2 goes here, 2. Okay, so right now we are having 1, okay, 1 over 1. Let me see. That is 1 divided by, okay, so 1 divided by 2 over 2 over pi sigma squared. So, which is the same thing as pi sigma squared divided by 2. Now, this is the variance of the median. Okay, that is the variance of the median. Okay, so the variance of the median is pi sigma squared. Uh, Let me see. Pi sigma squared. Okay, I think that's a particular n. Let me see. Oh, okay, 2n. The n right here. Okay, thanks for that. So 2n. So and that means I'm actually going to have a pi sigma squared divided by 2n. Okay, so we got pi sigma squared divided by 2n. Okay, so that is what we have for the variance of the median. Okay, so if this is the variance of the median, then what is the variance? Of course, I told you the other time, the variance of the mean. is actually sigma squared over n. Okay, so uh, the relative efficiency, the asymptotic relative efficiency that I call ARE. Okay, so I'm actually want to look at the variance, okay, of the variance of the mean, okay, divided by the variance of the median. Okay, so the variance of the mean is actually sigma squared over n, then divided by pi sigma squared divided by 2n. Okay, so mathematically, you're actually going to have a sigma squared divided by n multiplied by 2n uh, divided by pi sigma squared. Okay, n cancel n, or sigma squared cancel sigma squared, and of course we have 2 over pi. And of course, if you look at the 2 over pi, if you look at 2 over pi, 2 over pi, pi is 3.142, so which means this is strictly less than 1. Okay, so if this is less than 1, look at the ratio. It means for you to have a less than 1, then it means the variance of the median is greater than the variance of the mean. Okay, now if you take a look at let's look at 2 over pi is 0.64. Now, what are we trying to talk about? Okay, what I have to talk about, number one thing here is that when the population have is you know when the population is normal, okay, and you want to figure out average, okay, of course, it will be efficient if you considered mean instead of median, because if you take a look at what I'm seeing right here, the variance of the mean is less than the variance of the median. And you know what? That not only that, there's another thing we say. We're talking about asymptotic relative efficiency. Okay. Now take a look at the. This means 64%. Now it means, you know, uh, if median use 100% of the data, like use 100% data set, then it means mean, okay, we require the equivalent efficiency of the median using only 64% data. So if you take a look at that, it is not only that that this is efficient, but it's consistent in the sense that we're able to save cost of taking more sample. So which means mean is okay. Mean is okay in the sense that instead of you to, where median requires 100% data, the mean only requires 64% with the same efficiency. Therefore, I'm actually going to go for mean. I'm going to go for mean in terms of efficiency. I'm going to go for mean because I'm able to save the cost of sampling. Take a look at that. And that is what this is showcasing. So, and so that is the reason why I actually said that, sampling from normal distribution, the sample may perform as efficiently as a median, okay, using only 64% as many observations, okay? Take a look at that, okay? So it means for median to have the same efficiency, okay, for median to have the same efficiency, the median is actually going to use 100%, whereas the mean, we only use 64% of the data, as many as observation. Okay, so take a look at what I'm talking about now. Okay, which means whoever that's actually looking to get average, okay, you want to get average, and of course the probability distribution is normal, you got to go for mean. Okay, don't go for median. So mean will be more efficient, okay, and consistent. Now the next thing I actually want to talk about now is Laplace. When you're given a different distribution, like a Laplace distribution. Okay, when you're given a different distribution, probably like Laplace, there's a distribution in statistics called Laplace, which we also call double exponential. Of course, the Laplace distribution is actually lambda exponential raised to power minus lambda x minus theta, or divided by 2, and of course the range is from negative infinity to positive infinity. Now take a look at that. Okay, this is a Laplace distribution, and maybe probably we actually want to investigate. We want to find the average, and we feel like, okay, which of the mean and the median is going to be appropriate. The fact that the mean is appropriate for normal does not mean that the mean is going to be appropriate for other distribution. And that is the reason why we need to investigate, the relative efficiency of the estimators, okay, given the distribution. So for Laplace, the variance of x in this distribution is actually 2 over lambda squared, okay. Of course, if you really want to figure that out, you can actually use the variance of x using the expected value of x squared minus expected value of x all squared. Okay, so you can actually use that. So that has been done, and of course for Laplace, it is known that the variance of x is 2 over lambda squared. Okay, if it is 2 over lambda squared, uh, if the variance of x equal to 2 over lambda squared, then it means the variance of x bar, okay, is actually going to be 2 over n lambda squared. So the variance of the mean is actually 2 over n lambda squared for Laplace. Now, let us now figure out the variance of the median, okay, because we are actually looking for the one to use out of the two. Okay, give me 1 second. Now, let's investigate the variance of the median. And of course, if you want to get the variance of the median, okay, you're actually going to use 1 over 4 and f of theta or squared. Okay, now we need to get first obtain f of theta. Okay, so it's going to be lambda exponential raised to power minus lambda absolute value of theta, um, or theta minus theta divided by 2. This guy here is actually going to be uh, uh, 1. Okay, that's actually going to be 1. Okay, because exponential is power 0 is going to be 1, and of course the f of theta is going to be lambda over 2. Okay, so if f of theta equal to lambda over 2, you just need to come back here and write 1 over 4n. Okay, so lambda over 2 squared. Okay, so in that situation, of course, the variance of the median is actually going to be equal to, 1. If you want to simplify that now, going to have 1 over 4n, lambda squared divided by 4. So 4 cancel 4. Okay, so if 4 cancel 4, you're actually going to have 1 over n lambda squared. Okay, now the variance of the median is 1 over n lambda squared. Okay, so I'm going to clean this side now. Okay, so the variance of the median is actually 1 over n lambda squared, and don't forget the other time the variance of the mean is 2 over n lambda squared. Okay, so what I'm actually going to do now, then I'm going to find the relative efficiency. So now that I know the variance of the median, I know the variance of the mean using from the Laplace distribution, then what I'm actually going to do is to find the ratio of the two. Okay, now in finding the ratio of the two, of course, I can actually write the variance of the median, the variance of the median, um, the variance of the median. Give me 1 second. The variance of the median divided by the variance of the mean. Okay, So the variance of the median right here is actually 1 over n lambda squared. So divided by 2 over n lambda squared, and of course 1 over n lambda squared multiplied by n lambda squared divided by 2. So which means I got half. So A R E. Now when you take a look at this, in fact, I will advise that you do it this way. Give me 1 second. Or the other time, for consistency, I think we do variance of the median divided by the variance of the mean. I think that was what we did before, right? Although you can do any. So I'm gonna write ARE equal the variance, okay, the variance of the mean divided by the variance of the median. That was what we actually do before, right? Okay, but it can go the other way. So the only that your interpretation will actually be different. Okay, so the variance of the x bar here is 2 over n lambda squared divided by 1 over that. And of course, you're actually going to have 2 over n lambda squared multiplied by that over 1. So that's cancel that. And that is giving us 2. And of course, 2 is greater than 1. So when 2 is greater than 1, then it means the variance of the mean is greater here. So if the variance of the mean is greater, okay, it means median is more efficient than mean, when the probability distribution is Laplace. Okay. And what is the meaning of these two? Okay, so these two actually means two, or it means that you know uh if we a median require 100% as many observation, mean we require 200%. Okay, so 200%, um multiplying 2 by 100, and that will actually give you 200%. So which means you actually going to use more, okay, for mean to have the same efficiency as the median in Laplace distribution. Of course, where median use 100%, as many as observation, mean we use 200%, and that doesn't make sense, okay, because we actually also want to reduce the cost of sampling. Okay, so, and some of you could be wondering that, okay, why can't you reverse the ratio? Like, okay, some of you may be thinking in this direction, that of which decision are we going to take? You're actually going to see like situation where you considered the variance of the mean force divided by um, the variance of the median. Okay, of course, the variance of the mean, let me see, that was what we did before. I mean, the variance of the median force, if you consider the variance of the median force, so before the variance of the mean, so which means we're actually going to have something like this, right? That's going to be 1 over n lambda square multiplied by n lambda square divided by 2. Now we are having half here. Half is less than 1. And of course, if half is less than 1, it means the 1 in the denominator is greater. Now, how can we interpret half? If you multiply half by 100, just like what I said before, that is actually going to be 50%. And 50% will mean, uh, you know, you for with median, you're going to use 50% as many observation, and for me to have the same efficiency with median, of course, me will use 100%. So which means that's the double, just like what we had before. Okay. Uh, this is where I'm actually going to stop today, in case if there is anyone who actually need more clarification on what I did just discuss right now. Of course, you can actually reach out to me. Okay, so you can reach out to me, and I want to appreciate every one of you that will be watching the video, and of course, I hope you actually are going to enjoying it. But in case you need clarification of course, I can actually be rich. Okay, so I want to appreciate every one of you until on Friday that I'm actually going to come your way with another exciting topic in statistics. Make sure you stay safe and have a good day. So bye for now, guys.